This is Decaf-Math ASMR. I hope that you're doing well. Today we're going to take a look at Euler's Totient function. And I think I've made an intro to this idea before, but I thought we could come back and revisit it. We can look at more examples and come up with some new patterns and theorems. No proofs today, just some light fun applying Euler's Totient function. So as always, there's absolutely no pressure here. You can play along with what seems interesting. If you happen to be reviewing or studying this, I hope that it's helpful. But all in all, you can relax, enjoy, no pressure. This is not a lesson or a lecture or anything like that. I'm actually just excited to share this with you because this is a fun part of number theory, and it's just been a really long time since I've revisited it, so I hope that there are some discrete math lovers out there, and otherwise feel free to just close your eyes, relax, use this video to fall asleep if you need it. And if you see me looking down, it's because I am literally writing everything that you see right here. So you can pay attention to the math if you want, but otherwise just close your eyes and ignore me and let the math wash around you, okay? So here we have a table of different n values and the phi function, the totient value for those n. So we have from 1 through 100 here. But before we look at the actual values, let's define the totient function again, just to make sure we're on the same page. So instead of writing phi like this, I'm going to use this, phi of n. Hope that's okay with you, phi or phi. But I'm going to write it like this. So remember, a function takes in an input. In this case, n is going to be a positive whole number. So it's an integer, a positive integer. So 1, 2, 3, 4, 5, dot, 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 dot. So that's our input n. And this is, like we said, Euler's totient function. And the output is going to be, by definition, the number of positive integers less than n. That are co-prime or relatively prime. Those mean the same thing. To n. So it's the number of positive integers less than n that are co-prime or relatively prime to n. Now let me use slightly more mathematical notation just so that we can remember what this is about. So it's the number of m in the set of natural numbers such that the GCD of m and n equals 1. And m is going to be the numbers that are greater than or equal to 1, so starting from 1 and less than n. Okay, so what does this all mean? So, first of all, I want you to get a hang of this definition here. So, for positive integers, we're talking about our whole counting numbers starting from 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. that's this part. Numbers that are elements of the natural numbers, the set of natural numbers. So that part corresponds to this. And we are talking about numbers less than n. So that's where this less than n is. And we're talking about co-prime or relatively prime to n. So what that means is the greatest common divisor between m and n is going to equal 1. That means that m and n share no other divisors. So there are no other numbers other than 1 that go into both m and n. So by default, 1 is a divisor of all of these numbers because 1 goes into anything. So 1 will be the default one, but if there are no other common divisors, then the GCD is going to be 1. And so for each of those m, from 1 up until the n value, we just check 1 by 1, or we use some of these patterns that we'll develop today, but we check them and we want to know how many of these m satisfy this condition. So note that we just care about the number of them and not necessarily which ones in particular. Okay, so phi of n is going to give you the number of positive integers less than n that are co-prime or relatively prime to n. Okay, so I hope that that is a little refresher. If it's new to you, this might be kind of fun to think about. The key thing is to be very comfortable with factoring and finding common divisors, and we'll get some practice with that today as well, so no worries about it. But that's our general idea. So I guess first I can show the base case, which is 1. It's a little weird of a case because it's kind of like the only one that doesn't directly follow this definition. You can see here that for n equals 1, phi of 1 is going to be 1. According to our actual definition, we're looking for numbers that are less than n and greater than or equal to 1, but if n is 1, there is no number that is greater than or equal to 1 and also less than 1. So it's not exactly this definition. It's just kind of like our base case that we're going to assume. So let's say we're just comparing 1 and 1. So 1 and 1 are relatively prime because the only divisor that goes into 1 and 1 is 1. So this would be yes. And because of that 1, the number of numbers that are co-prime is 1. So that's how we get 1. Now that's just a whole bunch of 1s in this example, so it's not a very good one. But let's do a different number, and I hope that it'll give you a better idea. So let's do something like 8. I think that'll be a better example to see what we're doing here. So for 8, you can see that we have phi of 8 is 4. So what we're doing is we basically, if we were to do this all out by hand, we basically write out 8. We're comparing everything to n, and we take all the numbers starting with 1, and then whole numbers are positive integers. So 1, 2, 3, 4, 5, 6, and 7, and then we just go less than n. So here, note that actually technically you can go up to 8, but 8 and 8 will never be relatively prime because 8 will go into both of them, which is automatically not 1. So that's why we have a less than n on this side. You can just go up to n minus 1, just because you don't have to test 8 again. Also note that you don't have to do 1 either, because like we said, 1 goes into everything, is going to be relatively prime to everything. So we can just automatically do a check for 1. So 1 and 8 are relatively prime since the only number that goes into both of them a whole number of times is 1. For 2 and 8, are they relatively prime? The answer is no, because 2 goes into 2 once and 2 goes into 8 4 times. And so 1 is not the greatest common divisor, 2 is. Now the thing is though, in this case we know that 2 is the largest one, but in general if you can find any other common divisor, it's going to be greater than 1 because we're working with all positive numbers here. And so it doesn't really matter that you don't find the actual largest one. If you just find any common one between the two, it's automatically not going to be relatively prime. So there's just a little shortcut there. So for 3 and 8, yes, they are relatively prime because 3 is prime, so its only factors are 1 and 3. And so 1 automatically counts, but 3 does not go into 8 a whole number of times, so their greatest common divisor is going to be 1, so good there. 4 is not, because, well, 4 goes into 4 once, and 4 goes into 8 twice, so 4 is the greatest common divisor, but you might have noticed that 4 is even, it's a multiple of 2, so 2 is automatically a common divisor, not the greatest one, but it is a common divisor, which is already greater than 1. So 4 is not, and so 6 is also not, because 6 is a multiple of 2. So 2 goes into 6 and 2 goes into 8. So you might as well cross that out. 5 is relatively prime to 8 because 5 is prime and its only factors are 1 and 5 does not go into 8. So there are no common factors. And if you happen to be working with a larger number, it's totally okay to just list out all the factors if you need to. But in this case, the numbers are still relatively small. So you can use this little prime trick or multiples like 2, 4, 6 and that kind of thing. 7 will be indeed, because 7 doesn't go into 8 and 7 is also prime. So just use whatever tricks and shortcuts you can, since this process is a little tedious when you're doing it by hand. But you can see here we have 1, 2, 3, and 4. So there are 4 numbers that are less than 8 that are co-prime to 8. So that is why phi of 8 is indeed 4. Okay, so that gives you the idea. So that means, for instance, if I look at here, I have n is 63. There are 36 numbers that are less than 63 that are co-prime or relatively prime to 63. Okay, so as you can imagine, this has a lot to do with kind of factoring out these numbers, prime factoring out these numbers, because that will give you a good clue for what numbers are going to be relatively prime or not. A lot of times when you're finding the greatest common divisor or even least common multiples, it has a lot to do with prime factorization, since prime factoring is kind of like working with building blocks for the numbers. So you might as well just go back to the ABCs and build back from there. Now that we kind of understand what the function actually is and says, let's look at some fun patterns here. So we can see here that we have n going from 1, let's see, from 1, which is 1, through 100, which is 40. And one thing we can notice is that these numbers are all over the place, right? 40, it's not like it's linear or anything. There's an 82, an 88. For you statistics people, you can see what the mean, median, and mode are. It's a lot of work, but just note that it's not linear like that. And so kind of intuitively from the definition, you might think that would make sense because we're talking about relatively prime, so numbers that are already prime might have something unique about them. So let's look at prime numbers here. So from 1 to 100, we'll just do a few and I think we can catch a pattern here. But 2, 3, 5, 7, 11, 13, 17, 19. Hopefully I'm not missing any, right? 23, 29, 31, 37, 41, 43, 47. That's pretty good, don't you think? 53, 59. That's pretty good. Shall we finish it off? 61, 67, 71, 73, 79. And you thought that this whole time I was just reading off lists of prime to you in my ASMR videos, right? I'm just getting you ready for this video. Just kidding. I think that would be all. I'm thinking 90, 91, 92. I don't think so. I think we got them all. 97 I think is still one. Yeah. So I think this is all we'll look back through in a second here, but let's look at any patterns here. So phi of 2 is 1, phi of 3 is 2, phi of 5 is 4, phi of 7 is 6, for 11 it's 10, for 13 it's 12. Are you noticing something here? Always appears to be one less, right? And that indeed is a pattern. So if we have a prime number, then phi of a prime is 1 less this p minus 1. And in fact, I will one up that pattern if I happen to have an exponent of a prime, say 2 to the 3rd or something like that. So as long as this base number is prime, there is also a special formula for this. And that is p to the k minus p to the k minus 1. And another way to write that is to just factor out the p to the k. And this is just rules for exponents here. And that should give you the Totient value. So for instance, phi of 2 to the 3, which is 8, right? 2 cubed is 8. So phi of 8 is going to equal, you can just do 2 cubed minus 2 to the 3 minus 1 is 2. So this would be 8 minus 4, which is 4. Or you can use this version, which is just 2 cubed, which is 8 times 1 minus 1 over 2. So you just use that base prime value. Doesn't matter what that exponent is for this case. You just do 8 times 1 minus 1 half, which is 8 times 1 half, which is 4. So either way, phi of 8 is going to be 4. So you can do this for powers of prime numbers. So you can do, for instance, phi of, let's say, 3 to the 4th. So that's 81. Phi of 81 is 81. So that's still 3 to the 4th times 1 minus 1 over 3. Since the base prime part is 3. So it's 81 times 1 minus 1/3, which is 81 times 2/3. And this is just some arithmetic here, but it's this and this canceled to be 27. So 27 times 2 is 54, right? So if we look up 81, it should be 54. 54. Yes, nice. So you can do stuff like that, which is just so cool. Or you could just do 81 minus 3 cubed, which is 27. So 81 minus 27 should be 54 as well. So that's one other pattern. So I do want to end with the coolest one, I think, which is just a general formula for finding phi of n in general. So any n, not just primes or powers of primes. But before we do that, I wanted to share another property, which is that this totient function is multiplicative, in that phi of a times b is equal to phi of a times phi of b, but only if the GCD of a and b equals 1. In other words, if a and b are coprime. So this won't work if a and b are not coprime, but if you happen to have GCD of a and b is equal to 1, then you can actually multiply. So let's see if we can note that here, or have an example here. So I need two numbers that are relatively prime, and then hopefully we can confirm from 1 to 100. So we want their product to be less than 100. So let me see if I can just kind of come up with one. Let's say we have, how about, what's a good one? How about 9 times 11? So 9 and 11 are relatively prime. I chose this on purpose because 11 is a prime number. And 9 doesn't go into 11, so the greatest common divisor for them is 1. So phi of 9 is 6 and phi of 11 is 10. So phi of 9 times 11, which is 99, should equal phi of 9 times phi of 11. So phi of 99 should equal 60. So here we are, and there we are. It indeed is 60. So that's a fun one to mess around with here. Just make sure that A and B have to be coprime or relatively prime. Okay, and now for the fun formula. It's actually very similar to the power of a prime number formula, but let us write this out. It's actually so cool because it applies for all of these numbers. So phi of n is equal to n times 1 minus. So basically, if you were to prime factor n and you have distinct primes, however many, 1, 2, 3, however many, then you just take those primes. So again, it doesn't matter what power you raise them to, you just take the base prime number. So you take your original n and you multiply it by 1 minus 1 over p1 times 1 minus 1 over p2 times ... 1 minus 1 over pk. So 1 minus the reciprocals, and then you multiply all of that by n. So for instance, let's do one. Let's do phi of, well, let's just go ahead and do phi of 100 since we have it on this table. So you prime factor 100, and you can do that however you want. So 100 is 10 squared. You could do 4 times 25, so 2 squared times 5 squared. So just do that however you want to. If you do 10 squared, then 10 is 2 times 5. But you basically just keep factoring it until you have powers of prime numbers. And so here we have two distinct primes, 2 and 5. And so according to the formula, you take 100 and you multiply by 1 minus 1 over 2 times 1 minus 1 over 5. And this should be phi of 100. So let's calculate it out. 100 times 1 minus 1 half is 1 half. Times 1 minus 1/5 is 4/5. You just have to be comfortable with some fractions here. No big deal. Half of 100 is 50, so that all goes away to 50. And 50 times 4/5, you cancel that. So you have 10 up on the top, 1 on the bottom. So 10 times 4 is 40. So phi of 100 should be 40. And indeed, it is. So this formula works for any n value. So phi of n is equal to n times 1 minus 1 over p1 times 1 minus 1 over p2 times dot 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 1 minus 1 over pk, where pk and p1 to pk are distinct prime factors of n. Isn't that cool? Of course, there's so much more in the proofs themselves, but I think that this is a really fun result as we mess around with the Totient function. And I hope that you found this kind of interesting and cool. I think I will leave it here. If you are resting or falling asleep or asleep right now, I'm wishing you sweet, sweet mathy dreams. If you're continuing on with the rest of your day, I hope it's a good one. Let me know if you enjoyed this or if there are any other topics you'd like to see here on the channel that we can go back to, that we can explore together. I really do enjoy hearing from you, and I'm just jumping around. So we'll keep going with math and ASMR and math, and just stay tuned to see whatever I'm up to if you'd